workshop. We're very happy to have Peter Shore from MIT give the talk. And Peter needs no introduction, so let me just say that he's going to tell us about some very exciting recent work on building quantum money based on lattice assumptions. So thanks a lot, Peter.
Okay, thank you. This is the first time these slides have been used, so hopefully they don't have too many typos in them. And I want to thank the NSF and the Army Research Office for supporting me while doing this work. And let me start with an outline of the talk. And please don't hesitate to interrupt me at any point. I'm going to start out by giving a history and motivation for quantum money, and then some background in terms of a few theorems about lattices and maybe a little bit about quantum computation. We're not going to be talking about quantum gates here. We'll be using much higher level primitives, which I will talk about. I'm not going to tell you how to build these higher level primitives out of quantum gates because first, they're long and not very illuminating calculations. And second, it would take too long. So you're going to have to accept the higher level primitives, I tell you. I'm writing this paper, but it's not out yet. And finally, let me say that I really don't have a full grasp of the lattice literature. So it's maybe that some things I say can be done much more easily some other way. And if you feel like it, you can email me afterwards and tell me about these things. Okay, so what is the problem with money? The problem with money is that you can counterfeit it. And suppose you want to make money purely digital and you don't want any interaction. Well, that's absolutely impossible. But quantum states satisfy the no cloning theorem, which says you cannot make a copy of an unknown quantum state. So maybe you can use quantum states for money. And you might think that this will immediately let us use quantum states for money. And this was Wiesner's idea. I guess his original manuscript was somewhere around 1969, and it was first published in 1983 because he sent it off to somewhere and they rejected it, and then he sat on it for quite a while until Charlie Bennett, who was his friend from college, sent it off to SIGAC News, which is a non-refereed publication, and they published it. And his scheme had drawbacks, but it's quite a bit harder to come up with a quantum money scheme that doesn't have severe prior drawbacks. So people started doing this around 10 years ago. And what we want to do is give a new protocol for creating unforgeable quantum states that is based on the security of lattice problems. Okay, so there are proposals for quantum money. I think the first serious one was with me, and it's based on knot invariance, and it has not been broken yet. But on the other hand, I have no idea how many people have tried attacking it because it's based on the difficulty of a problem that I have that nobody has looked at seriously as far as I know. Arison and Cristiano proposed quantum money a few years later, but it's been broken. Mark Jandry proposed a complexity theoretic construction of quantum money. And I have heard that it's been broken, but I haven't seen the paper that actually breaks it yet, so I don't know its status. Daniel Kane last year, or 2 years ago now, proposed something based on modular forms, and I discovered this new scheme in November when I was writing up an inferior scheme to send off to stock. I discovered you could do a lot better, but of course I couldn't write up a completely new paper in 1 week, so I didn't send it to stock. So history, this is Wiesner's scheme. So in Wiesner's scheme, you put a sequence of quantum states in one of 4, polarizations, say vertical, horizontal, right diagonal, left diagonal on the bill. And anybody who does not know the polarization of these states cannot copy them by the no cloning theorem in quantum mechanics. And so it's secure. So what's the problem with Wiesner's money? Well, the mint knows the polarization, so the mint or whoever produced the money can check it. But you want the merchant to be able to check it without sending the bill back to the mint. And of course, if the merchant knows the quantization axis and eigenvalue of some of the qubits, then the merchant can verify the money. But it turns out that if the merchant has enough information to verify the money, then a coalition of merchants will have enough information to counterfeit the money. So this is the problem with Wiesner's money. Okay, so what we would like is some kind of verification procedure for some kind of quantum money that does not allow merchants to make counterfeit bills. Okay, I started thinking about this with, ideas from cryptography. So I guess everybody here knows this already, but for many years, cryptography was done with ad hoc cryptosystems, and lots of them were eventually broken. And over the last few decades, cryptography has become much more mathematical, and hopefully we're getting better cryptosystems now. And there are two kinds of proofs of security in cryptography. You can have.
Sorry, Peter.
Hello?
There was a question. Someone is asking what does verification mean in the context of quantum money? I think this was.
I will get to that. So I will get to that later. So you can have informationally secure cryptosystems and computationally secure cryptosystems. And the informationally secure ones is that no matter how powerful a computer your adversary has, they will not be able to break the cryptosystem because they don't have access to enough information. And the computationally secure cryptosystem says that the security of the cryptosystem relies on the difficulty of solving some computationally hard problem. So for quantum cryptography, the BB84 protocol for quantum key distribution can be proven to be informationally secure, assuming only that the laws of quantum mechanics as we know them are correct. So this solves a task which is impossible to perform classically with an informationally secure protocol. So this quantum money research started with me considering the question of whether there were any cryptographic tasks that a quantum computer might be able to perform with computational security and which were completely impossible for a digital computer to perform. And we came up with this task, quantum money. And of course, after I came up with the task, I spent several years trying to come up with a protocol for this task. But the task is that we would like one of the players in the protocol, and we will call her the mint, to maybe able to make a quantum state and a verification procedure P sub I, which goes with a quantum state. So these quantum states have serial numbers on them, so that first, if you apply the procedure to the quantum state, it says yes, at least with, almost certainly we can allow for an exponentially small chance of failure. 2, the test PI does not destroy the quantum state. Again, will allow you to have an exponentially small chance of failure. And 3, a potential counterfeiter holding both the state, or the quantum money state, and knowing the protocol for verifying it cannot produce 2 quantum systems, possibly entangled, that both pass this test P sub I. So this is what it means to verify quantum money. It's a test that can be passed by the quantum money, but which no counterfeiter can produce 2 quantum systems that both pass the test. So it's really anyone thing, but can anyone create money? I will get to that. Yes, anyone can create money, but not, I mean, not quite. So in fact, in our not invariant protocol and in Kane's protocol based on modular forms and in our lattice protocol, we believe that not even the mint can efficiently make another quantum state that also passes the test P sub I. So let's see. And this property is called public key quantum money by Scott Aronson, which I'm not entirely convinced is the right name, because what key is public in this thing? And Mark Jandry is calling something very closely related quantum lightning, because lightning never strikes twice in the same place. And our scheme satisfies this. So how do you use unforgeable states as money? Well, the Mint makes quantum states, and it gets pairs of money and serial number. And then it publishes somewhere, which cannot be tampered with, this list of valid pairs of, or valid serial numbers of the money, together with the protocol for verifying each serial number, which is actually, in this case, is very easy to compute given the serial number. And then it hands quantum money out, these quantum money states out together with I to any customer who is willing to buy its quantum money. And now if someone wants to create new forged quantum money, well, they can do the same procedure the Mint does, and they will get a random serial number, and it won't be on this list of serial numbers, so it won't be valid quantum money.
Peter, can I ask a question just as a cryptographer? So you have a different validation procedure for each I?
Well, I mean, basically, it's a different validation procedure, but it's essentially you input I to this program and you apply, do the same thing, except where I comes, you apply a state dependent on I. So it's actually a different thing, but it's very easy to go from I to the validation procedure.
Okay, so the validation procedure depends on I in some sense.
Right.
Yeah, okay, got it. It's like in Miller's talk. Yes.
Okay. Any other questions? So then anybody with a quantum money who knows I and has a quantum computer can check that it is indeed a valid quantum money state on the list, and that it passes the test piece of I. And another use for these unforgeable states is that you could put an unforgeable state into a ID card, and then these ID cards might be stolen, but you could not forge them. So you know that this is valid identification. Of course, for actual practice, for both money and quantum ID cards, you need to have quantum states that last longer than a few minutes. So one possible question is, could this property be of some use? Could our quantum money states be of some use as a subroutine for other quantum cryptographic protocols that don't require such long quantum states? And I think Mark Jandry has said something about this, but I'm not going to go into it. So how does our quantum money protocol work? Well, the outline is, first we will sketch our first candidate for quantum lattice money, and then we'll explain why it doesn't work. Then we'll sketch our next quantum candidate for quantum lattice money and explain why it still doesn't work. And then we'll sketch our current candidate and sketch the proof that it works. And we will all be doing this at a very high level. So our primitives are not going to be, quantum gates, but bigger operations, which I will tell you about. So first, I need to say something about lattices. And I expect everyone, at least everyone in this workshop knows this, but I think there are probably some quantum computation people who may not know about lattices listening to this talk. So I'm going to go into this. So a lattice is just the set of integer combinations of n vectors in n dimensions. So it looks something like this. And the difficult problem that I will be basing on money on is, given a basis of long vectors for a lattice, find a basis for short vectors. So these blue vectors are supposed to be a basis for long vectors for a lattice. And these two little red vectors are supposed to be short vectors. And the difficulty is going from the blue vectors to the red vectors. And the famous algorithm for this is the Lenstra and Lovász algorithm, which finds a basis exponentially longer in the dimension. So the dimension of this is always going to be n, small n, then the shortest possible basis. And I don't think there are any algorithms today that do better than exponentially longer than the shortest possible basis. So if you have a lattice, there are certain things you can do with it. So one of these that we will need is bounded distance decoding. So suppose you have a vector x that is very close to some lattice vector, then we can find the lattice vector in polynomial time. So what does it mean? What does very close mean? It means exponentially closer than the shortest vector in the lattice. So that's bounded distance decoding, which is one of the primitives we need to use for our protocol. Another primitive is Gaussian sampling. If you have a big enough ball around some point x, you can sample lattice points in this ball with probability proportional to a Gaussian, where the e to the minus the distance between the center of the ball and the lattice point squared over 2 times the standard deviation squared. And what does big enough mean? It means that sigma, the standard deviation, should be exponentially larger than the shortest vector in the lattice. And now what you can do with this Gaussian sampling algorithm is you can quantize it. So if sigma is exponentially larger than the shortest basis, you can find a superposition of lattice points and a Gaussian ball around some given point in quantum polynomial time. And this is the state of the superposition of lattice points, V with the amplitude on V proportional to e to the minus V minus x squared over 4 sigma squared. And of course, there's a normalization constant that we won't go into, but it's easy to compute. And to do this, you do exactly the same technique as Gaussian sampling classically, except you do it in quantum. Okay, so now there's a subclass of lattices that I guess Lior Eldar and I looked at. And this subclass is, well, first let's pretend P is prime. Actually, in our papers, it's not, but it's much easier to think about if it is prime and everything goes through pretty much the same way. So consider lattices n dimensions on a p to the n cube of integers. So everything is done mod p, where there's exactly one lattice point in each hypercolumn. So that red line will have one lattice point on it. Then there are going to be p to the n minus 1 lattice vectors in a cube. And here p isn't necessarily prime, although you can assume it is for the intuition. So we also need to define the dual of these lattices. And the dual lattice is a set of all vectors which are perpendicular to all vectors in a lattice. And here, perpendicular will mean x dot v is a multiple of p. So this is scaled up by a factor of p from the normal definition of a dual lattice. So this dual lattice will have one vector in each hyperplane, so there will be p lattice vectors total. And for the dual lattice here, L perp, each lattice vector is a multiple of any generating vector. So the lattice vectors are all one-dimensional mod p.
So Peter, just a clarification.
Yes.
So when you talk about hyperplanes and earlier hypercolumns, so there's a preferred direction that depends on the lattice along which these hyperplanes and hypercolumns are taken?
No, any axis parallel hyperplane or hypercolumn should have this property.
Okay, but there's more than p of those, but it's still, I see, it's still the case that there's a total of p. Okay.
Yeah.
Yeah, thanks.
Okay. And I want to claim for the original lattices, if the short vector problem is hard in arbitrary lattices, it is still hard in these lattices, even if p is only exponential in n. So this is something we proved in our paper. I think you can probably get it from other lattice theorems about lattices. And now we have a quantum Fourier transform on these lattices. And this is where the magic comes in. So this quantum Fourier transform is really only, it's only delta different from the regular quantum Fourier transform. And you can prove properties of this quantum Fourier transform by using the properties of the regular quantum Fourier transform. But it's very, thinking about this quantum Fourier transform as a primitive makes this lattice money really much easier to understand. So the quantum Fourier transform takes a vector in the lattice, and it takes it to a superposition of vectors in the lattice. So the lattice, it maps the lattice to itself, and the equation for this transform is that x goes to normalization e to the minus 2 pi I x dot y over p ket of y, or the quantum state of y. So this is the Fourier transform. And you don't really need to understand the Fourier transform here. You need to understand the properties of the Fourier transform. So I already talked about Gaussian superposition. A Gaussian superposition of lattice points around some point is just the superposition of all lattice points around that point with the amplitude decaying according to a Gaussian. And of course, this Gaussian can be, can have a standard deviation, which is small or large. And the properties of the Gaussian Fourier transform is, suppose you start with a Gaussian superposition of lattice points around L around 0. So this first thing is supposed to represent the Gaussian superposition of lattice points around the origin. It takes it to a superposition of the Gaussian superpositions of lattice points around each of the points of the dual lattice. So to reiterate something I said before, the dual lattice is sparse. There's only p points in it. And the lattice has p to the n minus 1 points in it. So it's much, much, much denser. So there are lots of lattice points near each point of the dual lattice, and a Gaussian superposition of lattice points around the origin goes to a superposition of Gaussian superpositions of lattice points around each of the points of the dual lattice. And if the original Gaussian superposition has a large standard deviation, then the Gaussian superpositions around each point have small standard deviations, and vice versa. If the original lattice point has a small Gaussian superposition has a small standard deviation, the Gaussian superpositions around each point of the dual lattice have large standard deviations. Okay, and does everybody understand this? Because this is really, the central, well, one of the central things in the way that the algorithm works. So are there any questions so far? Okay. And the next property we need to
Peter, sorry, there was a question in the Q&A which asks is the total number of vectors over which the superposition remains constant when you do the Fourier transform.
Yeah, because yes, because it's really a superposition over all vectors. It's just a lot of them have, amplitudes very close to 0, and the lattice points, the superposition is over the lattice points in the primal lattice in both of these.
Yeah, thanks.
Okay.
So sorry, Peter, this is Umesh. So the Fourier transform you're doing is mod p, right? So it's a discrete Fourier transform that you're doing. Yeah.
Yeah, the Fourier transform I'm doing is mod p. Yeah, because e to the minus 2 pi I x dot y over p.
Yeah.
If x times y is a multiple of p, then this is just 1. So, maybe explicitly it's not mod p, but we're just applying it to the lattice vectors in the p to the n grid, and it's, and it's mod p, yeah.
Peter, quick question. This is Vinod. I should think about the lattice as being super dense, right? The primal lattice, like p to the n minus 1 out of p to the n points. And the dual lattice is super sparse.
Yes.
Okay, sounds good. Thanks.
Okay. And I should say that the standard deviation of the large ball times the standard deviation of the small balls is equal to n over 4 pi. I don't know if I put that equation in, but I should have if I didn't. Now, there's another property. Suppose you start not with a Gaussian ball centered at a dual lattice point of 0, but a different dual lattice point. You still get Gaussian balls around each dual lattice point, but the Gaussian ball around the dual lattice vector W has a phase on every point in it. It has the same phase on every point in it. And that phase is e to the minus 2 pi I v dot W over P. And yeah, I mean, I'm not going to give the equations that prove this because, you know, they take a long time to go through and they're not particularly informative, but this is what happens. So now I think I have enough to describe the simple algorithm. Okay. So the simple algorithm, the quantum money state, is a Gaussian superposition of points in a small ball around a dual lattice vector W. So how do we create it? Well, what we're going to do is we're going to start with a large Gaussian ball centered at 0. Now we take the Fourier transform. We get a lot of small Gaussian balls around each dual lattice point. And what we're going to do, because the original lattice is super dense and the dual lattice is super sparse, you can create a large Gaussian ball with the Gaussian sampling algorithm. And now when you take the Fourier transform, you get a lot of small Gaussian balls around each dual lattice point. And now you can use bounded distance decoding to find the nearest dual lattice vector, because these dual lattice vectors are very sparse. So almost all the amplitude in this Fourier transform, which is these dual lattice vectors, small Gaussian balls around each dual lattice point, have are close enough to the lattice point that the bounded distance decoding will work. So we get a superposition of Gaussian balls around each dual lattice point. We can then use the bounded distance decoding algorithm to find the nearest lattice point and then measure that lattice point. And that gives you a superposition of a small Gaussian ball around a dual lattice vector W. So this is how you create the quantum money state. And our first algorithm, which I should say does not work, but it's, you know, the algorithm that does work is just, you know, builds on this. So you need to understand this first. So how do you verify the quantum money state? Well, there's a lot of things you can do that will, you know, answer yes if it is a, you know, a superposition of quantum. If it is a superposition of lattice points near this in the Gaussian ball, there's a lot of things you can do which will say yes. So one thing you can do is you can check that all the points in the superposition are near this dual lattice vector, and that's good. And now you can do something like take the Fourier transform and shift the lattice balls and measure the overlap, and you hope that that, you know, is something that you cannot counterfeit. So there's one possible objection to these verification tests. And if we do something like the swap test, well, the money will not pass the verification test with probability 1. which means that verification destroys the quantum money state. So the solution to this is going to be to use statistics to enhance the probability of the verification test, so it is close to 1. And the easy way to do that is to make the money be many copies of small Gaussian balls. And because you cannot create Gaussian balls at the same lattice point more than once, you will get Gaussian balls, each one centered at a different lattice point. And then you can do statistics and see whether each of these tests is passed with the probability you expect. And if it is, then the whole thing will pass the verification test with probably nearly 1. And if it's not a good quantum money state, the whole thing will pass the verification with probably close to 0. So this means that because with statistics, we're making the probability of passing the verification test close to 1, there is a standard technique in quantum computing which says we can do this and not destroy the original quantum state. Oh, I see a bunch of questions.
Yeah, they all have to do with the, you haven't told us what is the classical information that's associated with the quantum money state. So what was AI earlier, and how that allows you to do the verification, like how to be.
Okay. So the classical information is a dual lattice vector, W here. So your quantum money state is a Gaussian superposition and it points around a dual lattice vector. The classical information with serial number is a dual lattice vector. So the first thing you do when you get your quantum money is you measure that you measure and ask, is this state close to the dual lattice vector? And if it's not a superposition of states close to the dual lattice vector, you will have a reasonable probability of getting a no to this verification test. So now you know it's a whole bunch of states near the small Gaussian ball, or near the dual lattice vector. And then you want to do some other thing to make sure it's a small Gaussian ball and not some other collection of states near the dual lattice vector. And we don't know how to do this with this lattice money, but I will tell you that later. Okay, so
and so the BDD is solved using just the public basis for the lattice that parameterizes the quantum money scheme.
That's right.
Okay. So is it, did Peter answer everyone's questions? So those who asked questions? I guess if no one speaks up, we can continue. Thanks, Peter.
Okay, good. Okay, so I'm going to tell you why you shouldn't be able to copy first, and then I'm going to tell you why you actually can copy. So first, why should you not be able to copy this? Why can you not counterfeit this money? Well, suppose you could copy it. You could sample. Okay, let's pretend I am a counterfeiter and I've successfully copied the state. I can sample from the superposition of Gaussian superposition of the original and sample from the Gaussian superposition of the copy. And what I get are two lattice vectors, which are both close to W. And now if you subtract these two lattice vectors, their difference is close to 0. And I found a short vector in the lattice, which we know we cannot do unless you can find arbitrarily short vectors in an arbitrary lattice. Why is this? Well, I mean, what you could do is you could take any lattice and anybody can make a quantum money state. They won't have the right serial number, but it doesn't matter. And then if there's an algorithm for copying states, then anyone can get an original state and a copy. And if they're both superpositions of superpositions of vectors in the small Gaussian ball, then when they measure it, they will get two lattice vectors, which are both close to W, and their difference is close to 0, and you have a short lattice vector. So that says that you cannot copy Gaussian superposition of lattice vectors near a dual point if this Gaussian superposition is not really huge. So why doesn't this protocol work? Well, the reason is we don't know how to distinguish between having one lattice vector near this dual lattice point W and having a Gaussian superposition of lattice vectors near W. So what the counterfeiter could do is just measure one lattice vector from the Gaussian ball and produce arbitrarily many copies of that. And because we can't distinguish between this one vector near W and the Gaussian superposition, this counterfeiter has succeeded. So that's bad. So we need to improve this protocol. So how do we fix this? Actually, I think I should stop for questions here. Are there any questions? Okay, either everyone is understanding or I've lost everyone so far. But
Actually, Peter, can you go back to the test that you did? So.
Oh, but this test, it doesn't matter what this test is because it doesn't work at all. So we don't care what this test is. The point of this slide is if there's some probabilistic test, then you can make it deterministic by using statistics. But this test doesn't work, so I don't see why I need to talk about it.
So Peter, another question. So just to recap, the serial number is a dual lattice point W, right?
Right.
And the state is a superposition of lattice points around in a Gaussian ball around W, and this the Gaussian ball is pretty small, right?
It's small enough you can use bounded distance decoding. That doesn't mean it's really small. I mean, it could be, it could have a whole bunch of lattice points in it.
Right, yeah. Right. But I mean, sort of, it's exponentially. So the radius is exponentially smaller than the minimum distance of the dual lattice.
That's right. But of course, P is exponentially large, so you can make this. Yeah. You can make this a fairly large Gaussian ball, even though its radius is exponentially small.
Fair.
Well, I mean, fairly large be in relative terms of the number of points in it. Okay, so how do we fix this protocol? So what we're going to do is we're going to use a superposition of two copies of two Gaussian balls around two dual lattice vectors W1 and W2, and we'll let L be the vector between them. And now, what happens when we take the Fourier transform? Well, remember the Fourier transform of small Gaussian balls around a dual vector is a superposition of large Gaussian balls around each dual vector. And these large Gaussian balls all have different phases. And what that means is that the phases from the small Gaussian ball around W1 interfere with the phases when you take the Fourier transform of the small Gaussian ball around W2. And what happens? Well, so each of these big balls, there's the same phase on each point, and it comes from the actual lattice point that the small ball was around. So when you add the phases for W1 and W2, some of them cancel each other out, and some of them add. And I do not have time in this talk to go through the calculations, but you can make the probability that you see a point with x in the ith coordinate proportional to co-squared 2 pi x over p. And now we can observe this interference because this period is much larger than each of the width of each of these large Gaussian balls. So the fact that all of these large Gaussian balls have the same phase, or actually they're not the same phase, now the same amplitude, well, that's going to shorten, that's going to squash this cosine curve down a little bit, but not by very much. So you can observe this interference. On the other hand, if this interference, if this if this cosine was, had lots and lots of peaks and valleys, and it was much smaller than each of these large Gaussian balls, it would be completely washed out by the fact that the phase is the same, or the amplitude is the same over all this Gaussian ball. So how do we choose L? So what we're going to want is we're going to want a vector L in the dual lattice such that L dot V is the first coordinate of V. And remember that the phase was e to the 2 pi I W1 dot V and e to the 2 pi I W2 dot V. And what that means is because W2 is equal to W1 plus L, because L is the difference between these 2 points in the dual lattice. If we choose the vector L this way, we will get exactly one cosine curve, or the probability of seeing a given lattice vector is proportional to this cosine curve, and then we can actually observe this interference. And this thing, the vector L, is easy to find. You choose any vector W in the dual lattice and choose L equals W of 1, the first coordinate of that W, times W dot W inverse times W. And now L dot W is equal to W of 1 times W dot W inverse times W dot W, which is just W of 1. And this is mod P, I should say. But yeah, all these computations are mod P. Okay, no questions? So this is the second algorithm. It still doesn't work. So why doesn't it work? Well, it doesn't work for the same reason that the first algorithm doesn't work. What you can do is you can find a vector L prime in the original lattice that is very close to L. And in fact, that vector is L minus E1. And you can check that L prime equals L minus E1 is orthogonal to all vectors in the dual lattice. Because, okay, I should have put this equation down. We have L dot V equals V of 1. And now L minus E1 dot V is, well, the first thing is L dot V minus L minus E1 dot V is L dot V minus E1 dot V, and E1 dot V is V of 1. So this equation means that this lattice vector, which is very close to our lattice vector L, is orthogonal to all vectors in the dual lattice. And now a counterfeiter can just choose two vectors U1 and U2, which are close to W1 and W2, and use 1 over root 2 U1 minus U2 as the counterfeit money. And of course, they can find a vector that is close to either W1 or W2 by measuring this, quantum state, which is the quantum money state. It will, half the time it give you a vector close to W1, half the time it will give you a vector close to W2. So half the time it gives you U1 and half the time it gives you U2, but then you can compute the other one because U1 minus U2 is equal to L prime. So this doesn't work either. And since we know U1 and U2, we can make as many copies as we like. So how do we fix this? Well, what we're going to do is we're going to change L. And what we're going to do is we're going to choose L such that L dot V, remember we originally chose L such that L dot V is equal to V of 1. Now we're going to choose L such that L dot V equals alpha times V of 1, where alpha is going to be something close to the radius of a small Gaussian ball. And when we find L prime, well, we have the vectors L and L prime differing by an amount comparable to the radius of a small Gaussian ball. So the average of a sample of points cannot be at the center of the Gaussian balls W1, W2. Okay, so this, I guess, is, remember L was a dual lattice vector. So L prime differs from the dual lattice vector by the amount comparable to the radius of a small Gaussian ball. So here is our L vector, and here are these two Gaussian balls whose superposition is our quantum money. Now our counterfeiter is going to take L prime, and L prime is going to be nearly exactly L, but the difference between L prime and L is roughly the radius of this small Gaussian ball. And now, when the counterfeiter produces these points which differ by L prime, well, either the average of these, okay, so again, the money is not just going to be one of these pairs, but many, many, many copies of these pairs, each with two different small Gaussian balls differing by L. And now when the counterfeiter produces these, then either the average of the left balls will not be centered at the dual of the lattice point, or the average of the right balls will not be centered at the dual lattice point, because we know that the difference is not exactly a dual lattice vector, but something close to it, but differing by this radius of the small ball. And that means that we can test whether these averages are right. And if they're not, we will reject the quantum money. Okay, so so the other thing we have to do is we have to check what happens after the Fourier transform. And now there are alpha periods of this cosine function in the Fourier transform, where alpha was this L dot V equals alpha V of 1. Alpha was the radius of the small ball. But remember, P over alpha is roughly the radius of the large Gaussian balls, if alpha is the radius of the small Gaussian balls. So now this cosine function, which is the probability of actually seeing a point in this Gaussian ball, is comparable to the width of these Gaussian balls. And that means the interference isn't washed out completely. If a period was much smaller than the width of the Gaussian balls, then the interference would be washed out enough that we would not be able to observe it. But since the period is roughly the same width as the Gaussian balls, the verification still works and the interference isn't washed out completely. Any questions so far?
Yeah, can you explain again why this attack always gives you an L prime that, if I understood correctly, so you have many copies of the state, so you can do many measurements that will give you pairs that are shifted by some L prime. Why isn't L prime on the average?
Well, so you're not actually, so what your counterfeit money is many pairs 1 over root 2 U1 minus U2, where the difference between U1 and U2 is L prime. So how do we make the counterfeit money? Well, I mean, we originally had these Gaussian balls W1 and W2, and our quantum money was a superposition of these small Gaussian balls W1 and W2. Actually, this minus should be a plus, but let's not worry about that. So what the counterfeiter does is measure this superposition W1 and W2, and he either gets a U1, which is close to W1, or gets a U2, which is close to W2. But if it's a U1 close to W1, he can find U2 by adding L prime to it. and L prime is a vector in our lattice. So if U1 is a lattice point close to W1, then U1 plus L prime, which is U2, is a lattice point close to W2. So the counterfeiter measures these superpositions W1 plus W2, and then he gets a point which is either close to W1 or close to W2. So that's either U1 or U2. And then he computes the other U from whichever U he got.
Yeah. Yeah, that's
Okay.
okay. So, okay.
Good. So there's one thing I haven't told you about, which I actually, I see I have enough time left. I should have put it in my slides, but I didn't think I would have that much time. So I didn't. And that question is, how do we make this superposition of dual lattice vectors W1 and W2? And the answer is that we, do compute the state, have a state alpha 0 plus beta, alpha 1 over root 2, 0 plus 1. And what we're going to do is we're going to, okay, so actually it's a little bit complicated, but it's a variation of a very standard trick in quantum computing that will let us compute a random pair of, measure a random pair of Gaussian balls with difference L, even though we don't actually have, I can't do it without writing down the equations, and I don't have the equations written down, but it's a fairly standard trick in quantum computing. Okay.
So Peter, something like, it's perhaps a simple thing, but why can't I sort of choose a W1 myself, W1 and W2 myself, which differ by this kind of, this sort of L, and sort of, so why can't I create the sort of the money state by myself? Is sort of the question. The problem is that the job of the counterfeiter is to replicate exactly the W1 and W2 that he's given. Is that?
Yeah, that's the problem. The problem is that the counterfeiter has to replicate exactly the W1 and W2 he's given, and he can take the quantum state and he can measure it, and he can get a superposition of two Gaussian balls which differ by L.
Yes.
But they will be random. W1 will be random, and W2 will be W1 plus L. So he basically gets a quantum money state with a random serial number, and he is trying to get a quantum money state with a serial number that is a valid quantum money state.
Mm-hmm.
And there are exponentially many dual points. So the chance that he actually gets the right quantum money state is very small.
Thanks.
Okay. So I think that's the end of my talk, and it's just around right time to end it, so that's good. So what are the challenges? Well, one thing you can do is, I haven't done anything about optimizing the time and space required for this quantum money scheme beyond making sure it's, all the values are polynomial, and you could try to improve it. I actually think you can do a variation of Marriott-Watrous and get the size of the quantum money states smaller, although it will take more time to verify them, maybe. But I haven't worked that out. I don't even know if it works. Another thing you can do is come up with other quantum money schemes. So, we have, I think 3 or 4 quantum money schemes that work right now. And there's zillions of computationally hard problems you can make into cryptographic protocols. You can, ask, is there a quantum money scheme for another cryptographically hard problem? And You can also ask, are there other cryptographic protocols which are impossible classically, but which can be done on a quantum computer? Okay, thank you.
Okay, so thanks, Peter. I think I'm the only one who can clap, but everyone else is clapping. So let me say that, so Shafi Golwasser, director of Simons Institute and one of the organizers of the program, is going to give us some closing remarks in just a couple minutes. But maybe before that, we can take a few short questions. If there's more questions, we'll take them after the closing remarks. So anyone who wants to ask a question, you can type it in the Q&A. If you're an attendee, you can also raise your hand and I'll unmute you so you can ask your question. So let's take a couple questions and then we'll hear Shafi and then we'll take any more questions after. So maybe I'll start while everyone is thinking about it. So I had one question. So, I mean, in the talk, you just described why a particular attack is ruled out. So in principle, I imagine in the background, you have a theorem that says, you know, so it's two separate things to say, oh, it's impossible to clone the state. That's one theorem. And then another theorem would be, well, it's impossible to prepare any other state that also passes verification, right?
Yeah, so if you want a state that passes verification, it has to be
that has a valid serial number, yeah.
Right, if you want a state that passes verification, and it has to, so the question I can read is in the attack, why do we need a different L prime to counterfeit? Why can't we counterfeit with L? So if you have, if you want something to pass verification, it has to be a superposition of lattice points. L is not a difference between two lattice points, it's a difference between two dual lattice points. So if you take one lattice point and add L to it, you don't get a lattice point, you get a random point, which will not pass verification. So if you want the verification, if you want your counterfeit money to pass verification, then it has to be a superposition of A plus, it has to be a superposition of different lattice vectors. And if it's a superposition of different lattice vectors, there can actually only be one lattice vector in each ball. It can only have one lattice vector near W1 and one lattice vector near W2, because otherwise you could find a short vector in the lattice. So if you have one lattice vector near W1 and one lattice vector near W2, you need the difference between them to be L prime, some value, which is close to L, but which isn't L. And that's how we came up with L prime. And L prime actually works to counterfeit the money. I mean, this L prime that we come up with actually has more, I mean, just having an L prime close to L is not enough to counterfeit the money. It has to have more properties. But this L prime that we came up with actually has all the properties you need to counterfeit the money. So at that point, I almost gave up because I said, well, you know, things seem to be conspiring against me to make all the quantum lattice money breakable. But then I figured out the last step and fixed it.
So before we continue with the questions, I think maybe we'll hear the closing remarks. It'll be easier. So Hotek, do you want to say something? And then we'll continue with questions. So don't leave.
Thought sort of some closing remarks as the workshop organizer. So I just want to say on the behalf of my co-organizers, Schrader and Zvika, I want to thank all the speakers and all of the audience. So thank you very much. Also, a couple of administrative announcements. So we still have the Lattice seminars going on. Some of the talks that were postponed from the workshop will be moved to the Lattice seminars. There's also a special invited lecture by Daniele Michancio on lattices in about 2 weeks. So all this information you can find from the Simons calendar on the Simons website. And finally, all of the recorded talks will be on YouTube. You can find a link from the workshop webpage and from the Simons webpage. All right, so maybe let me hand over to Shafi for the closing remarks. If she's ready, if not, maybe we can take.
Yeah, I'm ready. Okay, so sorry, I was on mute. Hi, everyone. So I just wanted to say again, thank you all for coming. I think it was a great workshop. Just a little statistics. Apparently, there were 362 unique participants from 33 countries on the Zoom teleconference alone, and apparently over 2,000 additional viewers on YouTube. So I think we got a lot more exposure than if you were to come here in person. And this is even without counting today's attendance. Which I think we're around the 80s or high 70s. I think it's remarkable, the resilience of this community and the quality of the talks. I'm really grateful to everyone for putting such a tremendous amount of work into making things clear and accessible by a wide audience. I want to encourage you to show up for the quantum workshop next week. I certainly will, although this time rather than a expert or a proclaimed expert to someone who's really a novice. And other than that, we have teas, which are intended to the program participants at 11 o'clock, right? 11 or 11:30, Toma, I think it's 11 every day. So which is just a time to socialize. I don't think we're going to have it next week because of the workshop, and we didn't have it this week, but the following week. And as Hotek said, there are seminars, there are lectures, sort of for the wider audience that are being given. It's all on Simon's webpage. We're going to also start some podcasts that are sort of related to what's going on now, with some of the participants doing work actually related to COVID-19 and other things of interest. And I want to again say thank you to Shweta, to Hotek, to Zvika, to the co-organizers, Vinod, Daniele. I'm really humbled by how much you came together and, made sure that everything continues. So I'm optimistic, at least about our ability to continue doing science. And goodbye.
Okay, thank you.
Thanks everyone for coming.
Thank you all for coming. Yeah, so stick around if you have any more questions for Peter. All right, thank you all again. Bye.
Thanks, and on behalf of the attendees, thanks a lot to the organizers for setting up the workshop on short order and keeping us busy while we're sheltering in place. So thanks on behalf of those who cannot say it orally. So thanks a lot. Okay, so let's we can continue with questions to Peter now. That's one of the advantages of this online format, is that as long as Peter has energy, we can ask him questions. So Peter, I don't know if you had the chance to look at those that are on the Q&A.
Yeah.
And maybe take them in order. I think one of them you answered already. And
yeah. Okay, so there's one question: how do people authenticate the serial numbers and agree on what serial numbers are valid? So for that, well, what you can do is you can use some kind of classical authentication protocol, which is quantum secure. We don't actually have any clever quantum lattice way of doing that, but there are lots of ways of authenticating things, and we hope some of them are quantum resistant, so we can just use any protocol for authentication that we want. So which part of Marc Gendre quantum money is broken? I have just heard this from someone I believe is a reliable source, that it is broken. And I think if I went back to their email, I could probably figure out which part, but I can't tell you right now. And there's one more question.
I think the part that's broken is the concrete instantiation based on polynomials.
Yeah.
So it's not Aaronson Cristiano, it's the lightning, not the Oracle construction either. It's the concrete instantiation using degree something polynomials. I forgot, but I think there was a problem with that. Yeah, that's what I think. I'm not also completely sure.
That sounds right. So I don't understand this last question. Why can't we go from?
Do you want to speak up? If I find you, I can ask I can let the person allowed to talk. Okay, so if you want, you can talk. You just have to unmute. Okay, I can unmute you. No, you can unmute yourself. or just type it?
Yeah, you have to unmute him. I don't see how to unmute him.
I'm trying to do it, but nothing happens.
Okay, well, maybe if I go to the participants list, pull
Yes.
that up.
Okay. Yeah.
Oh, there.
Okay. Yes. No, yeah. So I was just wondering. So because it looks like you started with an original superposition, and then you created the quantum coin by some kind of transformation, the Fourier transformation.
Right.
So I was just wondering, like, what is public? Is public the quantum coin, which is just the target of this transformation, or what about where you started from? What is the status of that?
Well, you start from a superposition of, you start from a Gaussian superposition of a large Gaussian ball around the origin, and anyone can create that. And then you take the Fourier transform of that, and that gives you small quantum balls around each dual lattice point. And again, anyone can do that. And now you measure a lattice. You measure the closest lattice point in the dual lattice. And that gives you the Gaussian superposition around each dual lattice point. Or actually, you measure and get two Gaussian balls with distance L between them. And anyone can do that, but you're going to get a random pair of Gaussian balls. You're not going to get the actual Gaussian balls that match the serial number of the quantum money that you're trying to counterfeit.
So, so there's something hidden at the beginning. So what is this thing hidden which prevents me? I don't get that.
Oh, so the idea, what's random about this is when you make a quantum measurement, you get a random answer. And this random answer, the randomness in your answer is your serial number. So you get a random, quantum money state.
So I cannot decide the serial number from the beginning or something. It's just like it's a random process, and this will define me a serial number. Okay.
That's right.
Okay. Okay, thanks.
Any more questions from those who are left here? If it's easier to ask the question by speaking, you can raise your hand and I'll unmute you.
Yes, maybe I'll ask a high-level question. This is Evgeny. Sorry, this is all new to me, but just to check, I mean, I know you're still writing the paper. Do you think at the end you would be able, rather than kind of ruling out some clever attacks and responding to people, but say, okay, here is a lattice assumption, here is my definition of quantum money, here is a theorem that any attacker breaking quantum money breaks the assumption, or this is still beyond reach, it's too early in the game?
No, if you can break the quantum money, okay, let me take this back. If you can make arbitrarily many copies of a quantum money state for this scheme, then you can find a short vector in an arbitrary lattice. At least an arbitrary lattice of this form, which, since you can reduce any lattice to a lattice of this form, then you can find a short vector in an arbitrary lattice.
So that was also my question. Sorry, go ahead.
Yeah, go ahead, Tom. You will ask it better than me.
Well, it was also my question in a sense, what you took it back, right? So you said, so what you said is if you can copy the money states, then some lattice assumption is broken. But that's not the same as saying if you can break the quantum money scheme, then some lattice assumption is broken.
Well, I mean, copying the lattice, I mean, so we know how to, okay, we know how to create the lattice states. That's solid. We know how to verify the lattice states, and they verify. And so the theorem is if you can take one quantum money state that you have and that you know the serial number for, and turn that into 10 quantum money states that you have and you have the serial number for, then you can find short vectors in a lattice.
Right, but a separate attack could be creating 10 states that are not copies of the quantum money state, but that still succeed when you run the public verification procedure on them.
No, I said that wrong. If you can create 10 copies of the quantum money state that succeed when you run the verification procedure on them, then you can find short vectors in a lattice. And probably the answer is if you can do it for 2, then you can break short vectors in a lattice. But there's something funny about 2 because we have 2 balls, and something might go wrong. But I'm going to work on it and see if I can prove it for just 2.
Okay.
I mean, to me, that looks remarkably close to the definition. One thing, and as I said, I apologize if I'm wrong. I'm just kind of complete novice in the field, but at least from the papers of Zandri, I thought, and as I said, it's remarkable if anything works. So this is, if you don't achieve it, it's totally fine initially. But my understanding is that he has, maybe ambitious, but he has a formal definition of quantum money, maybe some relaxation. So definitely when you write a paper, it would be really exciting. Well, the best case scenario, if you just prove his definition, that would be a cryptographically strong definition along the line what Tama was asking, but definitely would be great if you can at least say maybe how close you come, or exactly along the way that you said, say I'm breaking this specific definition, because for cryptographers, I mean, that would be like extremely valuable, not just to rule out, some cool particular attacks, but to come close to get it to satisfying some definition.
Yeah, I think I will be able to do that.
That would be amazing. Yeah, I realize it's early. It's given how many schemes were broken. It's just from our side, at least for people who are learning, it would be great to kind of at least appreciate the theorems before seeing the techniques and just seeing how close you came. That would be great if you can kind of match it with cryptographic definitions. That would be awesome.
Okay, great. Thank you.
So we have maybe one last question, Peter, in the Q&A, asking about what kind of lattice, do you know what kind of lattice assumption specifically security reduces to?
So the scheme I have right now, it reduces to a short vector problem. If you can break the money, you can find a vector which is, no longer than some polynomial times the short vector in the lattice. Probably, okay, I haven't tried to get that down to n, but I don't see why you couldn't get it down to, if you can break the money, you can find a vector which is no more than n times the shortest vector in the lattice where n is the dimension. And that is what the security is based on right now. And I don't use any other cryptographic assumptions.
Thanks. Okay, maybe we should release the speaker. Thanks a lot, Peter. Thanks for the talk on behalf of everyone.
Yeah, well, thank you. And I guess you're going to post this at some point?
Yes, so Umit is going to do that. It'll be posted as a link on the workshop webpage, and it'll also be on YouTube. So if you want a link to it for some other people, you can just give the YouTube link. I think this will probably take a day or two. So next week it'll be up on the workshop webpage.
Okay, great. Thank you.
Thanks a lot. Okay, thanks everyone.